40,000 to 80,000. I really want you to take a second and just sit with that number. According to research published in medical AI journals, that's the estimated number of annual deaths in the United States alone that are contributed to by diagnostic errors. It's a staggering, heavy figure, and honestly, it tells us that our current systems, despite the absolute best efforts of brilliant medical professionals, are completely overwhelmed. People are slipping through the cracks. But hey, there's a very real, very practical shift happening right now. Welcome to This Explainer. Today, we're taking a highly pragmatic look past all that science fiction AI hype to see exactly how computer vision and healthcare diagnostics is actively solving this deadly crisis. We're going to dive into the data, the workflows, and the gritty reality of how we teach machines to actually help doctors save lives. Here's our roadmap for This Explainer. We'll start with the healthcare volume crisis, then cover teaching machines to see. After that, we'll compare human versus AI workflows, uncover the hidden implementation hurdles, and finally, wrap up with a healthcare AI playbook.
Okay, let's jump right in. Section 1, the healthcare volume crisis. Before we even touch on algorithms, we have to acknowledge that healthcare diagnostics fundamentally has a math problem. Just think about the extreme contrast here. A single human radiologist working at the absolute peak of their cognitive ability might review 50 to 100 complex scans in a single shift. An AI-assisted system? It can process thousands in that exact same time frame. We really have to frame this correctly right off the bat. AI is not some robot doctor coming to replace human clinical judgment. It's the ultimate high-speed sorting mechanism. It handles the crushing volume, flagging priority cases, and filtering out the routine stuff, so the physician can focus their precious cognitive energy on making the really hard calls. And man, that sorting mechanism is desperately needed. To put this into perspective, in the United Kingdom, the NHS imaging waiting lists have actually exceeded 1.5 million patients at various points recently. Across the developed world, imaging volumes have just massively outpaced the radiologist's workforce. The math just doesn't work anymore. We've got a massive backlog and patients are left waiting. When you combine that immense volume with intense time pressure, human readers are forced to work faster. And naturally, when humans work faster, they occasionally miss incredibly subtle early-stage signs of disease. It's literally like trying to find a needle in a haystack while someone is standing there holding a stopwatch. We're talking about a faint nodule in a lung CT, a tiny irregularity in a mammogram, or the earliest signs of glaucoma in a retinal image. But computer vision models? When they're trained on early-stage positive cases, they're specifically tuned to catch exactly these subtle, easily overlooked, life-saving details, and they do it without ever getting tired. Section 2, teaching machines to see. So, how does this technology actually tackle that backlog from a technical standpoint? At its core, computer vision in healthcare means teaching machines to see medical images and pull out clinically meaningful information. The whole pipeline starts with data. We're talking enormous quantities of imaging data collected over years, carefully annotated by domain experts. Essentially, the experts are telling the model, hey, this region is a tumor, or this opacity right here is pneumonia. The algorithms are then trained on these massive labeled datasets using deep learning architectures. They mostly use convolutional neural networks, which, if you think about it, basically act as highly advanced digital magnifying glasses perfectly suited for recognizing spatial patterns. Now, what's genuinely mind-blowing here is the sheer, overwhelming variety of data types these systems can process. It's not just one type of scan. Sure, we're looking at X-rays, MRIs, and CT scans in radiology, but it goes way beyond that. It extends out to analyzing pathology slides at the cellular level, detecting skin cancers from dermoscopy photos, spotting diabetic retinopathy in retinal images, and even guiding robotic surgical systems in real time through video feeds. It's an incredibly adaptable diagnostic engine. Section 3, human versus AI workflows. Understanding the tech is great, but how does this actually change a hospital's daily grind? Let's break down the real-world value here. Image review speed drops from minutes or hours per scan down to mere seconds. Consistency shifts from being highly variable between different human readers to a perfectly standardized, auditable baseline. Coverage goes from being delayed or completely reliant on on-call staff to continuous, 24/7 analysis. And perhaps the biggest game changer, scalability is no longer strictly bottled up by your human workforce. It scales instantly with computing power. Again, to be super clear, this isn't eliminating human clinical judgment. It's massively scaling the speed, consistency, and coverage surrounding that judgment. Section 4, hidden implementation hurdles. Okay, time for the complication. We really have to ask this seriously. If the technology is genuinely this good and the need is obviously this dire, why is implementation so incredibly hard? Well, the tech itself is actually maturing super fast. The real friction points, they're organizational, regulatory, and deeply technical in ways that rarely make the splashy headlines. Let's look at the gritty reality of hospital bureaucracy. First up is the regulatory red tape. In the US, the FDA classifies most of these diagnostic AI tools as software as a medical device, or SOMD. That means they require formal clearance before anyone can use them clinically. And the pathway for this, it demands extensive validation data, rigorous performance benchmarks across all sorts of demographic subgroups, and sometimes really complex comparisons to existing devices. It is an incredibly time-consuming and resource-heavy process. Next, we've got to consider what these AI models are actually plugging into. Most hospitals are running on legacy picture archiving and communication systems, PACS, using standards that were literally not designed with AI in mind. Honestly, sometimes these systems barely handle a basic software update. Trying to get a modern, cutting-edge computer vision model to successfully talk to this legacy spaghetti code and return structured, usable output into an electronic health record, that requires heavy, custom medical software development. It is definitely not plug and play. Then there's the data itself, which brings up an absolutely crucial point about equity. If a computer vision model is trained primarily on data from one specific patient demographic, it's going to inevitably underperform on others. It's a classic inputs and outputs problem. Like if a dermatology model is trained mostly on one skin tone, its accuracy naturally drops for other skin tones simply because it hasn't mapped enough visual examples. Building models that actually perform accurately across the board requires deliberate, comprehensive dataset curation right from day one. And finally, perhaps the absolute biggest hidden hurdle, human trust. Think about it. Even a mathematically perfect model will fail entirely if doctors refuse to use it. Explainability matters deeply here. Physicians are significantly more likely to act on an AI recommendation when the system can visually explain itself. By using tools like heat maps to highlight exactly which regions of an image triggered its output, the AI provides the why behind its flag. That bridges the gap between the algorithm and the clinician. Section 5, the Healthcare AI Playbook. Let's move to our final section and see how this all builds into a strategy. If you're a healthcare organization, what are the pragmatic steps to actually succeed here? Our sources outline a highly actionable playbook. Number 1. Define a highly specific, actionable problem. Don't just say, improve diagnostics. Say, reduce time to report for urgent chest x-rays. 2. Invest heavily in your data governance before you even touch a model. Your image archive quality literally determines your ceiling. 3. Run a low-stakes clinical pilot to measure real-world performance against benchmarks. 4. Consider hiring specialized healthcare IT developers who actually understand cloud platforms and legacy clinical interfaces. And 5, manage the human change. Getting referring physicians and radiologists to actually adopt the tool into their daily workflow is a massive project all on its own. Technical deployment is really only half the battle. I want to wrap up this explainer with a direct quote from our source material. Computer vision projects in healthcare are not a future possibility. They are a present operational reality in many health systems. This is the key takeaway you should leave with today. This isn't science fiction waiting in the wings anymore. It is actively fixing critical bottlenecks, addressing massive consistency problems, and closing access gaps right now. The diagnostic challenges in our healthcare systems are, quite frankly, monumental. But computer vision is proving to be one of the very few tools with the technical capability to make a measurable difference at scale. So I'll leave you with this. As the gap between early adopters and late movers rapidly widens in clinical medicine, which side of the divide will your healthcare system be on?